Moving on, we discussed display enhancement. So that's changing the way that an image is displayed. So the software package is essentially taking the original image, creating some kind of temporary image, and using that to display. But as I said, we never use those images in processing. It's strictly for the display purposes. Now, we're going to talk about image enhancement, and we will be using these images in subsequent data processing steps. And image enhancement is what gives digital remote sensing its advantage over analog remote sensing products. There's just only so much you can do with photo. You can look at them in stereo, you can magnify them, but you're basically stuck with whatever was recorded on the photo. That's what you got. But image enhancement allows us to go beyond that and highlight things like texture or remove image variability that might not be pertinent to the analyses we're doing. So these are processes that are typically used after radiometric and geometric correction. And we can divide these processes into those that spatially enhance images, that's what I'll talk about right now, and those that spectrally enhance images, and that will be the subject of the next lecture. So basic image manipulation, you'd think, well, it might go without saying, but I'm going to say it. One of the advantages of digital imagery is that you can easily zoom in on it. So this is an image from path 34, row 34. It's Landsat data, and it's 2002. And on the left, you're looking at it the full extent. Toward the right of the image, you can see that is the San Luis Valley. Okay, and so the fire that we're looking at here, and it is a fire, is in Durango. I put a little box on the left-hand side, and then we're zooming in. So it's one of the most simple, but sometimes you just forget. Oh wait, I could look at this under magnification, and I don't need to go and get a magnifier or change levels of magnification. Boom, I just click to magnify or zoom in or zoom out. It's done. And of course, we can continue to zoom in, and there you're seeing a fire. It's color infrared image, so the areas that are red are areas of vegetation, and you can see a river going through it with agriculture at the river bottom, and then the area of the fire itself in dark blue or black. So we're going to talk about spatial enhancement. And to understand spatial enhancement, you have to understand filtering and spatial frequency. So we're going to go through the mathematical process of processing image pixel data to emphasize spatial relationships between pixels. And so we're going to start with an image, and then the process will result in a grayscale representation of pixels that'll contrast spatial features, not in the sense of image contrast that we've used before, but rather, in the idea that whereas spatial pattern might not have been as obvious before, after the processing, it should be easier to interpret. So we use the concept of spatial frequency within an image. And spatial frequency is the manner in which grayscale values change relative to their neighbors. So if there's a slowly varying change in grayscale in an image from one side of the pixel to the other, like in the bottom right there, then that image is said to have a low spatial frequency. And you can think about it, it's the same idea as if you have a sine wave that has a long wavelength, or low frequency, it's slowly varying. Okay, whereas high frequency images have pixel values that vary very radically from adjacent pixels in an image or over a short distance. So this is the notion of high frequency and low frequency spatial variation. The next concept we use is convolution. So convolution involves passing a window. So a window in this case is just sort of a 3 by 3 matrix of pixels or values that fit over image pixels. We'll discuss this. I'll have a figure in a second. It'll make more sense. And we're going to pass that window over the image, and we're going to create a new image where each pixel in the new image is a function of the original pixel values and the values or coefficients in the moving window. And that's specified by the user. The window is more formally known as a convolution kernel, which you could think of as a matrix, 3 by 3 matrix of coefficients that will be multiplied by the image pixel values to derive that new pixel value for an enhanced image. The matrix can be of any size in pixels. It doesn't have to necessarily be square, although usually is. And convolution is actually the approach we use for both spatial filtering and resampling of images, as we talked about with geometric correction. So let's go through this in detail. So we have the kernel at the left, so that's just a 3 by 3 matrix, and within it are all ones. That's going to be an averaging pixel, because when we take the pixel values and multiply them by those ones, you're just going to wind up with the original pixel values. You're then going to divide by the number of cells in the kernel. So you're essentially adding all those values together in 9 boxes and divide it by 9. So this is a low pass or averaging kernel. So we're going to apply the kernel to each pixel and its neighbors individually. What does that mean? So here's our first target pixel. And that'll be the target neighborhood. So an area with the same shape as the kernel, but located over that first target pixel. And then we're going to just simply multiply the values of the kernel times the value of the image DNs. We're going to take its sum, in this case 23, and divide by 9, which is the number of pixels in the kernel. And we get a value, 2.56. That's the average value there. We do not put that value into the original image. What we're going to do is we're going to take that value and put it in the same location in a new image. Okay, so the kernel is sort of the convolution process is sort of a one-to-one. You look at the input values, you calculate a new value, you put it in an output image. So it doesn't affect the next calculation, which is moving on to the next target pixel. So here's a case, how you would go. You'd start with that upper left-hand pixel, and you move it around the image until every pixel has been evaluated using the kernel. Now you might wonder at this point, well, what do you do about the edge pixels? And we'll discuss that. So kernels can be any size. The larger the kernel, the more altered that central pixel is going to be. And larger kernels may have inverse distant weights to compensate. So for instance, if you're looking at the cubic convolution registration approach that we talked about earlier, it uses a 4 by 4 matrix, but the values near the center are higher than the the ones at the edges. So you get a larger influence of the pixels near the center. So we have various kinds of convolution kernels. We're just going to look at the simplest versions of those. You have a low pass or a smoothing, a mean kernel to the left. So that's always going to result in the mean being associated with the new pixels. And so it's going to smooth out the features. Maybe if you have a pixel that's a very high value or low value relative to the ones around them, that's going to be replaced by a value more similar to the adjacent pixels. So we have a high pass filter, okay, in the middle. And a high pass filter passes high frequency spatial variation. So if you imagine you've got an image sample that's 3 by 3 as well, and if all the values in the image are 1, then if we apply the high pass, the sum of the pixel values is going to be the same as the kernel, right? So it'll be, you have 8 negative 1s and 1 8 multiplied by all the 1s in the image. That's just going to give you 0. So what that's saying is there's no high frequency variability. To the extent that the pixels in the center, the pixel in the center contrasts with the pixels around it, you're going to get, well, if the center pixel is larger, higher value than the ones adjacent to it, then you're going to get a positive result for the high pass filter. If it's lower, then you're going to get a negative value. A high pass with add back, this is just the high pass filter, but with the value of 9 added to the central pixel. So what this does is your output image is sort of the original value plus that high pass filter. So this is good for visual interpretation mostly, where you're saying, okay, show me the original image pattern, but highlight the high frequency variation areas. And then at the bottom, we have an edge detection filter. So what we have there is positive values to the left, negative values to the right. And in the middle, we have this pattern of a positive value, -2, and then another +1. And if you look at this image, if you look at this kernel, and you imagine you're passing it over a feature that's a vertical line, okay? What's going to happen is those -1s are going to contrast with the +1s. Any difference between the left and the right is going to be highlighted because you're going to be contrasting, again, the negative values versus the positive values. If you have, on the other hand, a horizontal line, right, then the upper values, right, will be weighted by the same as the lower values. So 1, 1, and -1, 1, 1, and -1, and then however the middle turns out. And so you're not going to get a large value, okay? So we have a way to discriminate between horizontal and vertical changes in digital numbers. And so you could imagine that if you wanted to pick up roads that are oriented north-south or east-west, that would be one way that you could do it. There are also ways to select an angle and a way to find any edges, no matter what their azimuth. So let's look at the impacts. Here you have a low pass filter, so you can't really see, the original image is on the left. You can't really see the influence on the upper right-hand image, which is just a 3x3 filter. But if you look in the lower right, you can see that it's definitely smoother or blurrier than the original image at the left. And this is something you might want to do if you have a lot of speckle in your image and you want to get that out. High pass image. So again, the original image to the left, and then to the right, we have the high pass image. And so you get higher values wherever you have spatial variability. And then edge filters. So they're going to identify gradients or transitions between pixel values, road cuts, outcrops, edges of forest stands. There are many, many different approaches to this based on the direction of the edges that they consider, the sensitivity to edges, and then the kernel size that you use. So on the left, there's your original image. On the right, there's a 3x3 edge detector, simple edge detector. And then a 3x3 enhanced detection. And then at the bottom, you have the Spatial, which is sort of one of the most popular ones to go for. And you can see it really brings out those edges and gets rid of sort of the mean values. If you look at the reservoir there in black, the area to the south of that, and that's a burned area, in the Spatial processed image, you don't really see that distinction. You only see edges within it. And that's the concept. I told you we talk about border regions. So here we have a 3x3 window. If we apply that window toward the edges, then what's going to happen is some of the kernel elements are going to be outside of the border of the image. So there are lots of possible solutions. So you can just repeat the nearest valid output pixel. So, you can just bring in for the edge, for the pixels beyond the edge, the nearest smooth pixel and put it in there. You can reflect the input pixels outside the border. Essentially go on the other side of the edge row and pick up those values. You can reduce the window size at the edges, so only do, say, a 2x2 there. You can just not calculate values for the border region and set those values to 0 or mean. But the problem with that is if you have to do multiple filters, every time you do it, you're losing one row and column of edge pixels. And so on either side. So as a consequence, your image gets smaller and smaller. And so that's not really considered to be a good solution. And then, you know what? I've seen this suggested. I don't understand it, but some people have said wrap the window around to the opposite side of the image. So if you're down near the bottom and one of your elements is outside of the range of the image, just go up to the top of the image and pull the pixel that is most closely, that is on the same column, but the first row. Okay? Never understood it, but it's out there, so I thought I'd mention it. All solutions are just a trick to get around this problem. There's no real good solution to the problem of a border region for a 3x3 or larger window. You're just kind of stuck with choosing a bad solution.